Welcome to our presentation on the short paper Testing the Generalization of Neural Language Models for COVID-19 Misinformation Detection. I'm Jan-Philipp Wahle, and this has been a joint work with Nischal Ashok, who contributed equally, Terry Ruas, Norman Meuschke, Tirthankar Ghosal, and Bela Gipp. Since early 2020, the world is going through a global pandemic due to the coronavirus disease. One of the primary problems to reduce spreading the virus lies in the communication of proper protective measures and treatments. Online platforms can help spread correct information, but are as effective in propagating misinformation and building conspiracy communities. Examples for misinformation include questioning the effectiveness of masks or vaccines and reach all the way to recommending poisonous chemicals to cure the disease, such as bleach. This can not only lead to confusion, but to major harm in health, overloaded hospitals, and resulting high death rates. Thankfully, researchers worldwide have designed and implemented automatic misinformation detection models to counteract this problem. These solutions include detection models for treatment efficacy, conspiracy communities in social media, or fake news. We argue pre-trained detection models are maximally useful for misinformation detection when they're able to perform multiple tasks on different sources. We have seen a very similar trend in natural language understanding over the past years, in which models are evaluated on multiple tasks, such as question answering, paraphrase detection, or word sense disambiguation. For misinformation detection models about COVID-19, this generalization property was largely unclear. In this study, we answered the question of whether current detection models can generalize on different datasets and tasks. Therefore, we select 10 models from 3 different categories and pre-train 5 models on COVID-related data. Our 3 model categories are as follows. Category A contains out-of-the-box neural language models trained on general text before the pandemic. This category contains models such as BERT or Roberta, which serve as a baseline without any task-related or domain-related training. Category B contains models with additional domain-related data in the training dataset. For example, Category B contains BERT Tweet, representing a domain-specific baseline for Twitter data. Category C contains models that were trained on task-specific text. It contains, for example, COVID Twitter BERT, or CT-BERT for short, a model trained specifically on Twitter data and focusing on tweets about COVID. The training pipelines for each model category includes a pre-training and fine-tuning phase. From category A to C, each pre-training phase includes an additional component, allowing us to track the influence of components from one category to another. While general-purpose models from category A are pre-trained on unrelated text to the task, intermediate models in category B include related data from another domain on top of that. The training in category C includes a third training step on data related to COVID. The 6 datasets we chose cover a broad range of domains and tasks over approximately 1 million examples. All datasets are either sourcing from Twitter, news, or scientific articles. Detection tasks represented in our dataset include identifying misinformation about treatments or revealing misinformed communities. We performed 3 experiments to test the generalization of COVID-19 misinformation detection models. First, we test different classification methodologies. We compare static word embeddings with frozen weights of dynamic models and adjust model weights during fine-tuning. Evaluating 7 techniques on the COVID-CQ dataset, we find that fine-tuned transformers provide a significant advantage over their frozen and static counterparts. Transformers achieve up to 80% in F1 macro, which is 9% higher than static and frozen dynamic embeddings. This experiment shows fine-tuning transformers is superior to other methods we tested, which justifies our model choice for further experiments. Our second experiment tests whether tokenizers that are aware of a COVID-19 vocabulary, for example including words like corona, COVID, or booster shot, improve the model's capability in classifying misinformation. Our intuition is that if more recent terminology is available to the model during training, the performance may increase. Here we show 2 examples of 2 frequently applied transformers, BERT and Roberta. We find no significant advantage using a pre-trained vocabulary on the COVID-19 dataset. In our experiments, we even observe a decrease in F1 macro scores by up to 5%, although we expected a slight increase. We assume the scientific terminology is difficult to generalize to token relations on social media, which causes the drop in performance. More experiments are needed in the future to confirm this hypothesis. For this study, we choose to use general-purpose tokenizers. Experiment 3 contains the full evaluation of models and datasets. In Experiment 3, we fine-tuned model weights and use a general-purpose tokenizer as a result from Experiments 1 and 2. We observe COVID-19 models perform better in more than 60% of experiments. However, their improvement is small. COVID Twitter BERT only performs 4% better than BERT on the Twitter-based CMU Miss-COVID-19 dataset. The best general-purpose baseline BART can keep up performance with the specialized model COVID Roberta on the Twitter and news-based recovery dataset. Intermediate trained models from category B, such as bioclinical BERT or BERT Tweet, cannot provide better results than general-purpose baselines in all experiments. Measuring performance of specialized models on datasets from other domains, we observe opposite trends. Their advantage in the same domain is their disadvantage in other domains. While COVID Twitter BERT outperformed other models on Twitter data, it performs significantly worse than category A model BART on the news-based COVID-19 FN dataset. The same is true for BioCovid BERT and CO8, which contains a combination of Twitter and news. Considering the 3 experiments, we find that models fail to generalize between domains and tasks. Within a domain such as Twitter, COVID-19 specific models can outperform baselines by a small margin. However, when transferring to new tasks and domains, models did not capture general features about misinformation to be more useful than general ones. To conclude, we performed 3 experiments using 15 COVID-19 misinformation detection models on a total of 6 datasets. We found that although specific models outperform general ones, their advantage is small and typically requires models to be trained on the same domain or task. We see this work as an important step to compiling a benchmark for COVID-19 misinformation detection, as pre-trained models are maximally useful if their detection works across domains and tasks. Finally, I would like to thank you for showing interest in our work. We would also like to thank the reviewers and program chairs for their constructive feedback on the paper, and you can find the code to reproduce our experiments on GitHub and more information about the first authors below.